Here we go. All right, so welcome back. First order of business is to go over the quiz problems. This should only take a couple minutes. So I have a copy of the quiz here. And we'll start with this question, which asks about putting numbers in scientific notation, okay? But there's a little additional phrase here which says we want to use the proper number of significant figures. So that means whatever the number of sig figs we start with, we better end up with that number. We don't want to change the number of sig figs just because we're converting to scientific notation, okay? So for this first case, how many sig figs are given in the number shown here in part A?
3.
That's a number given to 3 sig figs. So if we put it in scientific notation, we're still going to keep 3 sig figs. That's the idea. Now, how do I put it in scientific notation? I know that the decimal is implicitly right there after the 0. And if we move it over 1, 2, 3 places to the left, we'll get the number 2.49, which is our coefficient. And I'm writing it with 3 sig figs. Okay, I'm not writing it as 2.490 or anything else. So then what's my power of 10? 3rd power, right? So with this other one, how many sig figs do we start with? 3. The 2, the 3, and the 0 are all significant. And to put it in scientific notation, let's just move the decimal point 1, 2, 3 places over, this time to the right. So we're dealing with a small number, less than 1. We have a negative power here. 2.30, 10 to the minus 3. Okay? This last one, 100.0. How many sig figs are shown there?
4.
That would be 4 significant figures. So we move the decimal over 1, 2 places to the left. That's a positive power of 10. 1.000 is how I put the coefficient with 4 sig figs. And then what do we have? 10 to the 2, right? Pretty straightforward. Okay, let's do the next one, which is convert 35 years to units of seconds. So if you're about my age, we'll see how many seconds you've lived, okay? Let's take the quantity 35 years as our starting point. And then we're just gonna put a series of conversion factors in front of this until we have units of seconds for time. So we don't want to just do this in one step, going straight from years to seconds. We want to take some intermediate steps that we know along the way. Okay, so how about this? What will be the first thing that comes to mind when converting years to a smaller unit of time?
Days.
Yeah, we say 1 day. Wait, no, we don't want to say that. We want to say 365 days is 1 year, right? Forget about leap years for the time being, okay? Okay, then what do? We have days, because years cancel. What do we do next?
Hours.
Maybe we could go to hours, right? Because in every 1 day, we have 24 hours. That makes sense, right? Days cancel. What can we do next?
Minutes.
So we have hours, maybe go to minutes, yeah? So 1 hour, 60 minutes. Cancel out hours. And lastly, every 1 minute, 60 seconds, right? So we're taking 35 times 365 times 24 times 60 times 60, and then our units in the final result are seconds. And can someone tell me what we get numerically? What do we get for our answer? So a lot of you have this on your quiz. It's 1.1, 10 to the 9 seconds. 10 to the 9 is a billion. So if you're in your mid-30s, you've lived about a billion seconds. Okay? The last one here is converting a speed from miles per hour to meters per second. So 65 miles per hour is a common speed for speed limits on the highway. What's that in meters per second? It's good to get a sense of this. So we have 65 miles per 1 hour. That's how we can think about the starting quantity. It's already a ratio. And that means we have to convert both the time unit on the bottom from hours to seconds and the distance unit on the top from miles to meters. The distance conversion is just given to us. So we have 1 mile and 1,609 meters as the conversion. Miles cancel. And then we're going from hours to seconds. We already kind of see how to do that here, right? In 1 hour, we have 60 seconds. And notice I have to write it with the 60 on the bottom because I want hours to cancel out, okay? And similarly, we have, what am I saying? Minutes. Sorry, brain's fried today. 1 hour, 60 minutes, okay? And then in every 1 minute, we have 60 seconds. Okay, there we go. What does that work out to?
29 meters per second?
Yeah, you get about 29. So the speed limit on a typical highway is about 29 meters per second. Okay, any questions? I'm going to put the solutions on canvas too. So with that said, let's get back to the lecture. So remember, we've been on this, the same lecture for about, I want to say, two whole weeks, right? This lecture is on kinematics in 1 dimension. We've pretty much covered all the physics that I wanted to cover on this topic. So the rest of the time we're going to spend here is just example problems so you can get a better sense of how to use the kinematic equations we derived last week, okay? So here's an example for you, which we'll start with, that involves multiple objects in motion. So here's what's going on here. We have 2 cars at opposite ends of a long straight track. So we have a red car over here at x equals 0, and we have a blue car over here at x equals 1 times 10 to the 3 meters. So the length of the track is a kilometer, or 10 to the 3 meters. So here's what happens with these 2 cars. At t equals 0, the cars, which are both starting at rest, begin to accelerate towards each other, okay? The red car, this one over here, has a constant acceleration of 1 meter per second squared, and the blue car, the one over here, has a constant acceleration of -2 meters per second squared. They're accelerating in opposite directions going towards each other, okay? So we have 2 questions about this situation. One is, at what time do the 2 cars collide? You can see that they should collide at some point, heading towards each other, but how long does it take? And then part B, at what location X along the track are they going to collide at? So let me just get your sense. For part B, do we think they'll collide like exactly in the middle of the track or towards one end? Yeah, so the red car is accelerating slower, so we might expect it's not going to move as far as the blue car before they collide. So we don't expect to get right at 500 meters, maybe something closer to here, okay? So let's just see that it works out that way in our answer. Okay, so I mentioned this before, but when we have multiple moving objects, each one of them has its own set of kinematic equations, okay? We don't have just one equation that describes both cars simultaneously. So what I'll do here is I'll just use subscripts. B, that's the blue car. R, that's the red car. So pretty obvious, right? Now each car has constant acceleration. And that means we can use the kinematic equations, any one of them, to describe the motion of these cars. So what I'm going to pull out for the kinematic equation that's going to be most useful here is x equals x naught plus v naught x plus a half ax t squared. Okay, and what I'm going to do is I'm going to apply this equation to each car individually. So here, let's just really break that down. For the red car, what can I say about x naught, the starting position of that car? That's just something that was given in the problem. Do you remember?
0.
Yeah, that car starts at x equals 0, as shown in the picture on the slide. So initial position for the red car is 0. What can we say about v naught for the red car? That's the initial velocity.
0.
It's also 0 because the idea is both cars are starting from rest and then they begin to move towards each other. So this is just due to the fact that we start at rest. Okay. And then our acceleration for the red car, that's just given too. But what was it?
1 meter.
It's 1 meter per second squared, and it's positive. So that means, check this out, for the red car, we have xr, that's the position of the red car, so I'm putting the subscript to denote that, equals initial position 0 plus initial velocity, also 0. So the first two terms in the kinematic equation are both 0. And then we have 1/2 times its acceleration, which is 1 meter per second squared times t squared. So what does this allow me to do? Whatever value of t I plug into this whole thing, it tells me where the red car is located. So if I plug in t equals 1 second, that tells me where the red car is located at t equals 1 second, okay? And any time you can plug in. All right, for the blue car, what was the initial position? So they don't start at the same position, right? The blue car starts at the far right end of the track, right? This is just in the problem. What was the initial position?
10,000?
Yeah, it was 1,000. I'm going to write it as 1 times 10 to the 3 meters. That's where it starts off. Okay, what can we say about its initial velocity?
0.
It's 0. Yeah, that's correct. And what can we say about its acceleration? It's -2 meters per second squared. So it accelerates in the opposite direction. Okay? So that means for the blue car, the kinematic equation that we wrote down up here looks like this. X naught is 1.00 10 to the 3 meters. That's where it starts off. V naught is still 0, so the whole second term goes to 0. And then we have 1/2. And then we have -2 meters per second squared. That's our acceleration. T squared. Okay. So the first question is about when do the cars collide? What can I say about XR and XB at the moment when the cars collide? They equal each other. They're at the same location now. So what we can say is XR equals XB. So in other words, I'm going to set this expression equal to this expression, and there's a time involved, which we can then solve for. You all see that? So we have XR, which is 1/2 times 1, that's 0.5 meters per second squared, times t squared, equaling XB. That's this number, 1 times 10 to the 3 meters. And then we have 1/2 times -2, that's just -1 meters per second squared, multiplying t squared. So what we're trying to do is solve for t, remember. So what I'll do is I'll add this negative term to both sides, so I'll get rid of it on the right, and then I'll basically have 1 plus 0.5, which is 1.5 meters per second squared times t squared, equaling 1.00 10 to the 3 meters. So now I can solve for t. T squared is equal to this divided by that, 1.00 10 to the 3 meters over 1.50 meters per second squared. So if I want to get t, I have to square root, correct? So can someone crunch those numbers for me? It's basically 1,000 divided by 1.5 under the radical.
666.666.
Did you square root it?
Oh, no, yeah. Square root is 25.81.
Yeah, so you have 25.8, I'm getting like 25.82, we'll round that to 3 sig figs, however. And that'll be a nice 25.8 seconds. So that's how long it will take before the cars meet each other, okay? Remember, this is the really important part. When two objects meet at the same location, their x values are the same, okay? So that answers the first part, when do the cars collide? The second part is, where do the cars collide? So in other words, like, at what location x along the track are they going to collide? Anyone have an idea for how we could do that?
You just plug t into our position equation, right?
Yeah, I just plugged t back into our original x equation, right? Which one did I plug it back into?
It won't matter.
It won't matter. Either one will do. Do you see what I'm saying? Because if I plug in the time into my xr equation, I'll get something out. And if I plug it into the xb equation, I'll get something out. But I should get the same result out because they're equal to each other, right? Let's just verify that that happens, okay? So let's try it with the xr equation. That's going to be a half times 1 meter per second squared times, this is our t value, 25.82 seconds. Square that whole thing. Can someone just tell me what that comes out to real quick? Yeah, 333 meters. And that's what we expected, right? It's closer to the left end of the track than the right end where the collision happens. Let's just verify that if we do xb, plugging in the same time, we'll get the same answer. So that's 1,000 meters plus a half times minus 2 meters per second squared. Again, I'm just using this expression, and then we're plugging in the time, 25.82 seconds, and we're squaring it. So can someone just verify what that is? Yeah, so punch it into your calculator, you get the same result. That's actually a good way to check that you did this right, okay? So any questions on this example? Okay, so this idea will come up in future problems. Either two things colliding or one person catching up with another person, things like that. We set their positions equal to each other. Okay, so that was the first example. Now let's get into an example where there are multiple solutions, where you solve some kinematic equation and you don't just get one answer, you get two different answers, and you have to actually decide which one is the correct answer in context, okay? So for this example, I'll give you a free fall problem. So we have a ball thrown straight up into the air from ground level at an initial speed of 15 meters per second. The question is, at what time is the ball's height 5 meters? So this is kind of a poorly phrased question in a way, because it actually reaches that height twice, okay? It's pretty easy to see when you just trace the path out, right? You throw the ball into the air, and it hits that height while it's going up. Then it reaches a peak, comes back down, and then it reaches that height of 5 meters off the ground once again. So our equation, when we try to solve it, is going to actually tell us two different times. One time for this on the way up, and then another time when we reach the height on the way down. Now, which time is going to be bigger? So if we get like I don't know, 1 second and 3 seconds, I know the smaller time is when we're going up, right? Because that happens first. The bigger time is when we're going down. That happens later. So that's how we can distinguish these two cases. You all see that? Okay. Another way to visualize this is to graph position versus time for this projectile. So remember, this is an upside down parabola because we have acceleration in the negative direction when we graph this thing out. And if we just pick out the position y equals 5 meters, you can see that our parabola intersects twice with that. So once here when we're moving up, and then once again here when we're moving down. So let's just work out what the two times are, but hopefully we already understand how to interpret them. Right? One's on the way up, the other's on the way down. Okay, so let's do that real quick. So the height of the ball above the ground is given by this kinematic equation, which is y equals y naught plus v naught y times t, and then minus a half gt squared. So all we're going to do is plug in what we know into this formula. So y, that represents our final position, or in other words, our final height above the ground. What was that again? It's 5 meters. Y naught represents our initial position, which is 0. V naught represents our initial velocity. That's 15 meters per second, and that's multiplying t. And then we have minus a half times g. That's 9.8 meters per second squared times t squared. So that's kind of looking like a quadratic expression, isn't it? It's got a t squared term, it's got a t term, and then some kind of constant term. So that's a quadratic. But what I'm going to do is write this in the kind of standard form. Remember, for a quadratic expression, you want to throw all the terms on one side and just have that equal 0 before you try to solve it, okay? So what I'm going to do is I'm going to take these two terms that appear on the right side and then just throw them over here to the left side. So let's start with this one. I have minus a half times 9.8. That's minus 4.9. But if I add it to both sides, it's now over here as positive 4.9 meters per second squared t squared. And then here I have positive 15 times t, but I'm going to subtract it from both sides, which puts it over here, and minus 15 meters per second times t is that term. And then this 5 meters was already on the side of the equation, so I'll just leave it as so. Okay? So that's just to put it in the standard format where it's 3 terms added together equaling 0. So can you tell me, in the quadratic formula, we have a, b, and c. Which term is a, which term is b, which term is c? So let's start with a. Which of these terms is a?
Squared term.
It's the squared term, which means the coefficient in front of that is a. So 4.9 meters per second squared, when it comes time to calculate, is what goes in for a. Okay? What goes in for b?
Negative 15.
It's this negative 15. It's important to get your signs right. Okay? So when we plug in that b term, it has to be negative 15. And then our c term is the remaining constant term. All right, so we're solving for t. That equals, let's do the quadratic formula. What is it again?
Negative a plus or minus square root b squared minus 4ac.
So we start with negative b. So negative b plus or minus square root b squared minus 4ac over 2a. So let's put in what we know. Okay, negative b, that's negative minus 15 meters per second. plus or minus square root negative 15 meters per second squared. So when you square this negative number, it becomes positive. And then we have minus 4 times A. A is this number right here, 4.9 meters per second squared, times C, which is 5 meters. And then we divide all that by 2 times A. 2 times 4.9 meters per second squared. So you can crunch these numbers in your calculator and just verify that we end up with 2 solutions, one of which is 2.7 seconds, the other which is 0.38 seconds. So what do we interpret this as? The bigger time is when you reach the height of 5 meters on the way down, and the smaller time is when you reach that height on the way up. Okay? Because one obviously is going to happen first, right? So do we have any questions on this, how this works? All right, so there you have it. That's an example where we deal with multiple solutions. That will happen from time to time. Actually, this is a problem where we deal with both of those situations I just outlined. So more than one object in motion and more than one solution, and we have to sort of sort it all out after we do the math, okay? So here's what's going on. You are driving your car towards an intersection, and you're just going at a constant speed of 11 meters per second. There's a Porsche that stopped behind the line at a red light. So at the moment, when you're 15 meters from that line where the Porsche is, the light turns green, and the Porsche begins to accelerate from rest, because it's initially stopped, at a constant rate of 3 meters per second squared. You continue at the same constant speed. Okay, so you start out basically behind the Porsche, right? And you're both moving forward. But initially, the Porsche is moving kind of slowly, right? So you overtake it at first. But you keep moving at the same constant speed, and the Porsche keeps speeding up. So eventually, it's moving faster than you. So then it overtakes you. So those two things happen. First, you overtake the Porsche, and then it overtakes you. Can you envision that? Okay. So the first question says, how many seconds after the light turns green do you pass by the Porsche? That's when you overtake the Porsche. And how far from the stop line are you when that happens? And then the second question is, like I said, as you keep going, the Porsche eventually catches back up with you. When does that happen? So what time does that happen? And how far away from the intersection are you when that happens? Okay? So it's a lot to keep track of. So let's start with a picture. This is going to help us really nail down the equations. Okay? So first of all, we have 2 objects in motion. So we better, have separate kinematic equations for each one. But what I'm going to do is draw a picture of what's going on at t equals 0 when the light turns green. What's going on at t equals 0 is you are basically behind the Porsche, and the Porsche is just right behind the stop line at the intersection. Okay? And the distance between these 2 cars is 15 meters. All right? But we're going to keep track of where everything is using an x-axis. So what I'm going to do is draw an x-axis. That will allow us to keep track of both where you are and where the other car is located. Okay. So I'm going to put the origin of this coordinate system right there where the stop line is. And if you are 15 meters back from the stop line, what does that mean about your position right here? Yeah, I'd have to consider this to be negative 15 meters right there. Does that make sense? Again, as long as we're showing that they're 15 meters apart, we're good. But you're behind where the Porsche is. Okay, so at this moment, you are moving at that steady rate of 11 meters per second. And you're just going to continue moving that way the whole time. Okay? But the Porsche is not moving yet. Does that make sense? All right, so for each car, we're going to have a kinematic equation. And we're going to use the same one that we used previously, which is x equals x naught plus v naught x times time plus 1/2 ax t squared. The reason this is going to be useful, just like before, is whenever one car catches up with another, we'll set their x values equal. So that's why it's useful to have this kind of kinematic equation. All right, so let's start with your car, which I'm going to label with subscript y from here on out, okay? Your car. What can we say about your initial x position? That's x naught, x0.
-15.
That's negative 15 meters. That's your starting position. You see that? What can we say about your starting velocity?
11 meters.
Yeah, we agree. You're starting off moving at 11 meters per second. What can we say about your acceleration?
It's constant. 0.
It's 0. Okay, because you're moving at a velocity that's not changing, you just keep moving at 11 meters per second the whole time, you don't have any acceleration, okay? 0 acceleration. This is because you move at constant velocity. Okay? And that means x, y, that is the x position of your car, that's what we're saying here, is equal to x naught, which is minus 15 meters, plus v naught, which is 11 meters per second, times t. But then we just add 0 to that because you're not accelerating, okay? So as far as your position, it's just minus 15 plus 11 times t. Okay, let's do that for the Porsche. Say the other car, which we'll label with the subscript p. What can we say about the initial position? That's 0, right? This car starts off at x equals 0. What can we say about the initial velocity?
Also 0.
Yeah, so it starts off not moving yet, and it's only after it hits the gas and starts accelerating that it begins to move, so we have 0 initial velocity as well. And what about the acceleration? That's just what we're given, right? What was the value?
3 meters.
3 meters per second squared, yeah. So this means xp, x naught is 0, v naught is also 0, and then we have a half, 3 meters per second squared, t squared. Okay, makes sense so far? So what does it mean when one car passes another? Because we want to solve for the time when that happens. We have the following. We have xy equaling xp. Right? We have the same distance from the stoplight, basically. Okay? So that gives us minus 15 meters plus 11.0 meters per second t. That's xy. And then we have equaling xp on the other side, which is a half of 3, or 1.5 meters per second squared times t squared. So this is another quadratic, isn't it? So let's just go through the whole process of solving the quadratic equation. But again, we want to put it in that standard format where we just have all the terms on one side equal to 0, okay? So what I'll do is I'll put these two terms over here, That means I'm going to add 15, so it's positive, and I'm going to subtract 11 times t, that will be negative over here. So what I have is 1.5 meters per second squared t squared plus minus 11 meters per second t, so that's putting that term over there, and then plus 15 meters. I'm putting each of these things in parentheses just so I know that's what A, B, and C are all equal to, okay? So that's A, that's B, and that's C. So let's solve for t, the time when one car passes another. What do we have? Well, remember, quadratic formula is minus b. So in this case, b already has a negative sign, so it's now positive 11 meters per second, plus or minus square root b squared. That's minus 11 meters per second squared. And then we have minus 4ac. A is 1.5 meters per second squared. C is 15 meters. Okay, so I'm not writing down the formula, I'm just jumping straight to what the numbers are. And then we have 2 times A, which is 1.5 meters per second squared. So that involves a little bit of number crunching, but that's how you set it up. And I'll just tell you what the result is. We get 2 answers. One of them is 1.811 seconds. We'll actually keep 3 sig figs on that. The other is 5.223 seconds. So how do we interpret this? Again, the math is telling us that these are the 2 solutions, but we have to think it through to know which solution is the answer to our question. The question is, for now, what time do you pass by the other car? What time do you pass by the Porsche? That's what happens first, right? Because initially you're moving faster. You overtake that car. So that's going to be the smaller out of the 2 times, because that happens first. You see that? So the answer is, for the first question, you pass the Porsche at time 1.81 seconds. Okay? And then the other question associated with this is, where are you? In other words, like, how far from the stoplight are you when that happens? So we can plug this time, just like before, into either one of these expressions. It doesn't matter which one we choose. We'll get the same result. So, I don't know, let's do the expression for your position, which is minus 15 meters plus 11 meters per second, and then we're multiplying this value of t, which is 1.811 seconds. And can someone just quickly do that number crunching for me and tell me what it is? Yeah.
Why did we use 1.811 instead of 5.22? Or what's like the difference?
Because, again, what happens first is you pass by this other car, and so that's going to be the smaller of the 2 times, because that happens first. And that's what the first question is about. Okay? And can someone just give me that number, please?
4.92.
Yeah, so this is 4.9 meters. We actually keep 1 decimal place because we're adding here. So 4.9. So you pass by the Porsche pretty quickly. Okay? But we already kind of have the answer to the other question, which is the Porsche passes you later, at the later time, which is 5.22 seconds. Okay, so after it's moving fast enough, it's now overtaking you. Okay? We already found that time, so we don't need to do any additional work. Okay? And like I said earlier, if we want to know what the location is, where that happens when the Porsche overtakes you, we just plug that time back into one of these x equations. And we could choose either one. Let's do xp just to switch it up. That is a half times 3 meters per second squared, right? I'm just using this. And then we're putting in the time of 5.223 seconds, and we're squaring that time. And what does this work out to, everybody? Yeah, so it's like 45.8 meters, right? So we've solved the problem, we've answered all the questions, but I think it's maybe useful to look at this another way, just to make some sense out of the question. So we could, if we wanted to, think about plotting the motion of your car and this other car on a position versus time graph, okay? And we'll have a line on the position versus time graph for each one of those objects. Where the lines intersect with each other, that's when one object passes another, okay? So here, this is what we're gonna put some data onto, is a position versus time graph. So x in meters, time in seconds, right? Okay, if we do this for your car, this would be what we're graphing. We'd be graphing basically a straight line because there's just a t term and there's not a t squared term. This is a straight line. My slope, that would be my 11 meters per second. And my intercept would be this minus 15 meters. Okay, so for your motion, you start down here at minus 15 meters. But you're traveling in the positive direction at a constant speed. So it looks just like this when we graph your motion, okay? So that would be the motion of your car. What about for the other car? This would be a parabola, right? Because it's a t squared. And also, it starts right here at x equals 0. So we want to show a parabola going concave up, starting right here. I'll do my best to draw that, but it would look, I don't know, something like this. Yeah? So this is where you pass the Porsche. Okay? Because at least right after this, you're ahead of the Porsche, right? Your x value is bigger. But over here, that's where then the Porsche overtakes you. Okay? And if you're a big fan of cars and I've been like pronouncing that wrong this whole time, sorry about that. Okay, I'm sure I was. Okay, so does that make sense? This is just another way to look at it. All right, let's do some more examples. All right, here's an example for you. We have two runners going by the names Allison and Florence, who are competing in the 100-meter race. When the race begins, Allison starts by accelerating at a constant rate of 2 meters per second squared. But after Allison has accelerated for 50 meters, she stops accelerating, and then the rest of the race, she just goes ahead and runs at a constant speed. Okay? Then we have Florence, who just does this. She accelerates at a constant rate of 1 meter per second squared the whole time. And then the question is, who will win the race? Which one of these is a better strategy? Who's going to win the race? Okay. Does anyone have any just general ideas about how we could tackle this? What if we tried solving for the amount of time it takes each person to finish the race, and then just compare? That makes sense, right? Whichever person does the race in a smaller amount of time, they're going to win. So if we just have the two values of t for the two different runners, we should be able to answer the question, right? Okay, so let's work it out then. Let's work out how much time it takes each runner to finish the race. Okay. And just so we're kind of keeping track of where things are located, I'm going to draw an x-axis like this. This will be my starting line, and this will be my finish line for the race. I'm just going to put the starting line to be x equals 0, which means the finish line is x equals 100 meters. All right, so that's just our coordinate system that we're going to use to keep track of motion. So we have to do two separate calculations. Let's start with Allison. Okay. For Allison, we're going to break the motion into two parts. The reason we have to do this is because, remember, for the first part of her motion, she's accelerating, and then for the second half of her motion, she's not accelerating. So we're going to take those as two separate pieces that we'll put together at the end. Okay? So the first part of her motion is that for the first 50 meters, she's accelerating. Okay? So what are some just variables that we can put down that describe what she's doing in the first 50 meters? Well, let's start with x naught. That's her starting position, right? What would that be?
0.
Just 0? That means you're at the starting line, right? What about v naught? Also 0, right? If you're running a race, you don't get to start moving before the race starts, right? So you have 0 initial velocity, okay? What else do we know? What about the acceleration? So in the problem, the first 50 meters, she's accelerating at a rate of 2 meters per second squared. So that's the a value for that. And actually, we can do this as well. Remember, x naught represents the initial value of x. X without the subscript is final. So after she's covered 50 meters, x is just 50 meters, right? Make sense? So what I'm going to do is put that into the kinematic equation. X equals x naught plus v naught xt plus a half axt squared. I'm just putting the known values into that equation, okay? So x on this side is 50 meters. X naught, 0. This is v naught. That's also 0. So the first two terms on this side are 0. Then we have a half times a, which is 2 meters per second squared. And then we have t squared. So let's just be clear about what this t represents. That's the time it takes just for the first 50 meters of the motion, okay? It's not the whole time, it's just, let's call it t1, the first half, okay? So if I wanted to solve for t1, here's what I would do. A half times 2 is just 1. And then I would be doing 50 meters divided by 1 meter per second squared. And then I would be square rooting on both sides to just solve for t. So we're really just doing the square root of 50 here. What is that? Square root of 50?
7.07.
Yeah, it's like 7.07 seconds. So for Allison, she covers the first half of the race in 7.07 seconds. Okay? That makes sense? Okay, I'm going to do kind of a side calculation right now. I'm going to write down this kinematic equation. Vx equals v naught x plus axt. The reason I'm gonna bring this into the picture is I wanna know not only how long did that first part take, but how fast is she moving after covering the first 50 meters? We're gonna need that for later, okay? So, starting at 0, starting with an initial velocity of 0, and then accelerating at 2 meters per second squared, and then plugging in this time. This will tell us if you're accelerating at this rate for this amount of time, starting at 0 for your velocity, you'll end up with this velocity. So 2 times 7.07 is what?
14.14.
Yeah, it's like 14.1 meters per second. Okay, so that was just the first 50 meters. Let's do the last 50 meters. She's moving at constant velocity. Okay, that's what's going on here. So I'll do it like this. For the last half of the race, the starting position now is 50 meters, okay? We're starting at the halfway point, just if we're looking at this part of the motion right here. But we end up at a position of 100 meters, because we're considering moving from here to here. So x naught is 50, x is 100. Okay, what can I say about v naught x for the second part of the motion? It's 14.1 meters per second. Okay, so starting at this point, the velocity is 14.1 meters per second. And what can I say about the acceleration? It's 0, because she's moving at constant velocity for this last part. Okay? So put that into the kinematic equation. I'm going to just write it again. X equals x naught plus v naught x times t plus a half ax t squared. X is 100. X naught is 50 meters. V naught x is 14.1 meters per second, multiplying t. And then because our acceleration is 0, I'm putting in 0 for the last term. So 100 minus 50 is 50. So t is 50 meters divided by 14.1 meters per second. And I'm going to call that T2, because that's the time to complete the second half of the race. Okay? And what would this equal?
3.54, 3.5.
Yeah, it's like 3.57 seconds-ish. Okay, so the total time for Allison to finish the race, I'm going to call that TA, the total time for Allison to finish the race, is equal to T1 plus T2. So can you add these two together? 7.07 for the first half, 3.57 for the second half. What do we get for the total time? Yeah, it's like 10.6 seconds, something like that. Okay? Okay, that one took a little bit of time because we had to split it into these two parts. For Florence, it's a little easier because she's just accelerating at the same exact rate the whole time, so we do not need to break the problem up into two parts for her motion. Okay? So we got Florence. Okay, so I'm just going to do this in one chunk. She starts off with 0 initial velocity to start the race. She accelerates the whole time at 1 meter per second squared. That's just what we're given. And then she starts at the starting line, which is x equals 0, and she ends up at the finish line, which is x equals 100 meters. So we'll apply the same kinematic equation, x equals x naught plus v naught x times t plus 1/2 axt squared. For x, the final position is 100 meters. For x naught, the initial position is 0. For v naught x, the initial velocity is also 0. And then we have a half accelerating at 1 meter per second squared times t squared. And I'll call this TF because it's for Florence's time. Okay? So to solve for TF, if TF squared equals, I'll multiply both sides by 2 to get rid of this 1/2, and then we'll have a factor of 2 over here. That'll be 2 times 100 meters, divide by 1 meter per second squared, to put that down here, and then we just have TF squared by itself. And then if we square root on both sides, we'll get TF. And what does that equal? Just basically it's the square root of 200, right?
14.1.
Okay, so Florence completes the race in 14.1 seconds, and Allison completes the race in a much shorter time, 10.6. So clearly we have Allison wins the race. Do you agree? All right, do you have any questions on that?
So we're going to be using that same equation for every question that has multiple rooting on it?
I don't want to say every single one, but if there's ever a time in a problem where one object meets another object, collides with another object, or passes by another object, yeah, that would be the case. We just happen to find it useful here to figure out the time where each person finishes the race. Yeah. We could have, as with all of these problems, there's usually more than one possible way to get to the solution. So I just happened to pick a solution that involved that equation here. Anything else?
Is there ever going to be a situation where we have to use the quadratic and then we get 2 answers, but we only need one of them? And how would we figure out which one makes sense as far as that's concerned?
So that always is just going to depend on each problem specifically, right? So I gave you a few examples, like the object moving up and down, right? One time you found is when the object hits a certain height on the way up, and the other is when it hits that same height on the way down. The 2 cars example, right? We saw how to interpret each solution. So it just depends on the context of each problem. There's not really a general rule for that.
Could you kind of explain again like why you broke that first, like Allison's equation into 2, like where you have to find the velocity again?
Here's why. Because we can only use this equation here when acceleration is constant. So the acceleration is constant for the first 50 meters, but then it suddenly changes to 0 acceleration. So basically, while the acceleration is staying constant, we can use this equation for the first 50 meters. But once the acceleration changes suddenly, we have to just sort of break that into a separate part and use this equation again. Okay? So in other words, the value of A has changed. It was starting at 2 meters per second squared, and now it's just 0. So that's why. Okay, so you know what, I think we only have 5 minutes left, so I just want to point something out real quick. We're not going to do any more problems. We've reached the end of this lecture, and I just want to remind you that at the end of every lecture I have practice problems, okay? So there are a whole bunch of problems. You can pull these up on Canvas if you look at the slides. And these are questions that I've made. Usually if we have extra time in class, we'll spend some of that time going through these. But you can also use them to study, okay? And some of these come from previous exams I've given and previous quizzes I've given. I wrote all these questions, so it's useful just to get a sense of what kind of questions I might ask you in the future, all right? You can also find the answers to every one of these questions on Canvas. If you go to the files and then you go to lectures, you'll see the answer key for all of these, okay? So that's it. I'll see you next time.